Problem 95. Given a square-bottomed box whose surface area is 24 square centimeters, find the dimensions of the box so that its volume is maximized. Now the area of this box is given as the sum of the areas of the 6 faces. So this is the area of the bottom, which is x squared, plus the area of the top, which is also x squared, plus the area of the front face, which is x times y, plus the area of the back face, which is the same, plus the area of the right face, which again is xy, plus the area of the left face, which is the same. So this says that our area is 2x squared plus 4xy. Now since this area is equal to 24 square centimeters, we set this equal to 24. And this is our constraint equation. This is the equation that's fixed. So what we do is we solve the constraint equation for y, which gives us 24 minus 2x squared over 4x. We also have a formula for volume, that is the function we're trying to maximize. And a volume of a box is length times width times height. So this is x squared y. But we know from solving our constraint equation the value for y. So let's plug this in to the volume equation. We've got x squared equals 24 minus 2x squared over 4x. Simplifying this, we have v equals 24x minus 2x cubed over 4. This is the function we want maximized. So this is our objective equation. Since we're down to one variable, we can look at first the domain of this objective equation, and then we'll maximize by looking at critical numbers. So if we look at the smallest value of x that make physical sense in this problem, x can't be negative because it represents a length. So x could conceivably go down to 0. If we look at the largest x value, that means all of the area is spent on both the top face and the bottom face. So there is no height in this. If y was 0, then that means the area of the top will be 12 square centimeters, which says that x is then the square root of 12. So we've got our domain, we've got the function we're trying to maximize, so now let's take our derivative and set it equal to 0. V prime is then 24 minus 6x squared over 4, and we're going to set this equal to 0 to find our critical numbers. We can multiply both sides of this equation by 4, giving us 24 minus 6x squared equals 0. Then divide both sides of the equation by 6 to give us 4 minus x squared equals 0. This can be factored up to give us x equals 2 and x equals negative 2. Going back to the domain of the problem, x equals negative 2 doesn't make physical sense. So our only critical number is x equals 2. So now to determine if this is a maximum or a minimum, we're going to look at the volume at both endpoints of the interval, as well as our critical number. So we look at the volume at x equals 0, the volume at x equals 2, the volume at x equals square root of 12. If we plug x equals 0 into our volume formula, remember our volume formula was given here, if x is 0, the volume is 0. And that certainly isn't going to be a maximum. If we look at the other extreme, at x equals square root of 12, remember if x was the square root of 12, that means all the area was spent on the top and the bottom faces, so y is 0. And if y is 0, then again by this formula, volume is 0. Now looking at the volume evaluated at x equals 2, well, we know what the x value is. If the x is 2, let's plug that into here to get a value for y. So this is 24 minus 2 times 4 is 8, divided by 8. This gives us 16 divided by 8, which is 2. So now x and y are both 2. So this is 4 times 2, so our volume is 8. Now since these are the only candidates for maxes or mins, I know that the volume is maximized when x is 2. So the dimensions of the box are x was 2, y was 2, and the other x was 2. So our dimensions are 2 centimeters by 2 centimeters by 2 centimeters.